Hello students of class 10, this is your advanced mathematics, page number 115. In this video, I will start from 3.4.2 greatest common divisor or GCD. So this is definition 4 saying let A and B be two integers and d not equals to 0 is an integer such that d divides a and d divides b, then d is the common divisor or factor of a and b. This one we all know. A and b are two integers and d, which is not equals to 0, is an integer. If d divides a and d divides b, then d, I can say that d is the common divisor. Yes, d is the common divisor of a. D is the common divisor of a and b, or I can say that d is the factor of a and b. Yes, this one we already know. In here, illustration they have given. 3 is a common factor of -6 and 12. Yes, so 3 divides -6 and 3 divides 12. In here you see 3 divides -6 and 3 divides 12. Yes, so therefore 3 is a common divisor of -6 and 12. Okay, this one we already know. 1 is a common divisor of any two integers, that is, for any two integers a and b, 1 divides a and 1 divides b. Common divisor, or we can say factor. Now you see definition 5. Let a and b be two integers, at least one of which is non-zero. A positive integer d is called the greatest common divisor. Okay, greatest common divisor GCD of a and b if this d I will call it the greatest common divisor of two integers a and b if d divides a and d divides b. Okay, d divides a and d divides b. And next is for some integer c divides a and c divides b, then c is less than equals to d. The greatest common divisor of a and b is denoted shortly by GCD AB. According to condition 1 of the foregoing definition, definition 5, d is a positive common divisor of ab. Okay, for this one, d divides a and d divides b, I can say that d is a positive common divisor of a and b. And by condition 2, I can say that d is the greatest of all common divisors of a and b. Okay, so in here these things you have already learnt in lower classes. Okay, these things you have already learnt in lower classes. Just in here means we are getting definition here. Okay, we are getting this greatest common divisor, which is GCD. Okay, or you can take it as HCF, highest common factor, or you can call it greatest common divisor. Okay, so definition 4, it is saying that a and b are any two integer, yes, and d is another integer which is not equals to 0, because the divisor cannot be 0. Yes or no? Divisor cannot be 0. So d is another integer which is not equals to 0. And then if d divides a and d divides b, then I can say that d is the common divisor of a and b, or d is the common factor. D is the common factor of a and b. For example, like 3 divides minus 6 and 3 divides 12. Yes, so therefore 3 is the common divisor of minus 6 and 12. Now if I want to say greatest common divisor, okay, if I want to say greatest common divisor, for example, A and B be two integers, okay, A and B be two integers, at least one of which is non-zero. Okay, A and B are two integers, at least one of which is non-zero. Okay, now next, a positive integer D is called the greatest common divisor of A and B if D divides A and D divides B, and another integer, let's say C divides A and C divides B, okay, and C will be less than equals to D. Understand? The greatest common divisor of AB is denoted shortly by GCD AB. Okay, according to the condition, according to this condition, I will say that D is the common divisor of AB. Okay, and by condition 2 we can say that D is the greatest common divisor of A and B. That much only. This is definition 5, nothing there. Okay, D divides A and D divides B. Yes, D divides A and D divides B. That means D is the common divisor of AB. And if I give condition 2 also, yes, if I give condition 2 also, that means from condition 1 I can say that D is the common divisor of AB. And from condition 2 I can say that D is the greatest common divisor of AB. How I can say? In here saying that for some integer C, if C divides A and C divides B, and C is less than equals to D, okay, and C is less than equals to D, so by condition 2, D is the greatest of all common divisors of AB. Okay, so definition 5, one more time I am reading it. Let A, B be two integers, at least one of which is non-zero. A positive integer D is called the greatest common divisor of AB if D divides A and D divides B, and some another integer C divides A and C divides B, okay, then C is less than equals to D. Okay, the greatest common divisor of AB is denoted shortly by GCD according to condition 1 of the foregoing definition, that is definition 5. D is a positive common divisor of A and B, and by condition 2, D is the greatest of all common divisors of A and B. Okay, illustration here. Let us consider two integers minus 12 and 18. Positive divisors of minus 12 and 18 are respectively this 1, 2, 3, 4, 6, 12 and 1, 2, 3, 6, 9, 18. Okay, yes, positive divisors of minus 12 are this and 18 are this. Therefore, common positive divisors of two integers are 1, 2, 3 and 6. Clearly 6 is the greatest common divisor. 6 is the greatest among these positive common divisors. Thus GCD of minus 12 and 18 is 6. Okay, finished. Now next you see, next page, Theorem 4. For two integers A and B, at least one of which is non-zero, there exist another two integers x and y such that GCD of AB is equals to ax plus by. Very important theorem, this one. Okay, this proof we will discuss it later. We will discuss. Okay, in this video we will not discuss this proof. just you remember this theorem. Okay, theorem 4, it is saying that for two integers a and b, okay, for two integers a and b, at least one of which is non-zero, there exist another two integers x and y such that GCD of AB is equal to ax plus by. Okay, two integers there, at least one of which is non-zero. Okay, now there exist another integers x and y such that GCD of AB is equal to ax plus by. Okay, we will have to remember this theorem. This proof we will discuss, but not in this video. Next you see is definition 6, relatively prime integers. Okay, relatively prime integers. So relatively prime integers saying that two integers a and b, both of which are non-zero, are called relatively or mutually prime to each other if GCD of AB is 1. Two integers there, a and b, both of which are non-zero, are called relatively prime integers or mutually prime if GCD of AB is equals to 1. For example, 4 and minus 3 are relatively prime to each other since GCD of 4 and minus 3 is 1. Next you see theorem 5, two integers a and b, both of which are non-zero, will be relatively prime to each other if and only if there exist two integers x and y such that ax plus by is equals to 1. Okay, this is your theorem 5. Two integers a and b, both of which are non-zero. Okay, two integers a and b, both of which are non-zero, will be relatively prime to each other if and only if there exist two integers. Okay, there exist two integers x and y such that ax plus by is equals to 1. Okay, so in here you see proof. Let a and b be two relatively prime integers. Okay, first of all I will take a and b be two relatively prime integers, and I will show that ax plus by is equals to 1. Then conversely I will take ax plus by is equals to 1 and show that a and b are two relatively prime integers. That means in here you see a and b are two relatively prime integers. So therefore I can say that GCD of AB will be 1. Yes, GCD of AB will be 1 since a and b are two relatively prime integers, so therefore GCD of AB will be 1. Okay, now when GCD of AB is equals to 1, okay, GCD of AB is equals to 1, then I can say that GCD of AB is equals to 1. This one, since GCD of AB, I can write it as ax plus by. Okay, ax plus by for some integers x and y. Okay, GCD of AB is equals to ax plus by. This is, I am getting it from theorem 4. Okay, two integers a and b, at least one of which is non-zero, there exists another integer x and y such that GCD of AB is equals to ax plus by. Understand? This is I am getting from theorem 4. Okay, GCD of AB, I can write it as AX plus BY. So GCD of AB is 1. So therefore, AX plus BY is equals to 1. Finished? So in here, that one only A and B be relatively prime integers. Let A and B be relatively prime integers. Then I can say that GCD of AB is 1. Now GCD of AB is equal to AX plus BY for some integer x and y. This is I am getting from theorem 4. So since GCD of AB is 1, so therefore AX plus BY will be 1. Now conversely I will take, let AX plus BY is equals to 1. Let AX plus BY is equals to 1. Finished? Okay. And also let GCD of AB equals to D. Now GCD of AB is equals to D. Okay, therefore I can say that D divides A and D divides B. Okay, this is from where I am getting GCD of AB is equals to D, then D divides A and D divides B. This one you see. This one you see GCD of AB. Okay, a positive integer D is called the greatest common divisor of A and B if D divides A and D divides B. Okay, D is called the greatest common divisor of A and B if D divides A and D divides B. So in here, D is the greatest common divisor of AB. So therefore I can say that D divides A and D divides B. So therefore I can say that D divides AX plus BY. Yes, D divides AX plus BY. AX plus BY, this is from where I am getting D divides A and D divides B. Then I am saying that D divides AX plus BY. This is from where I am getting. This is I am getting from, you see this one. Theorem 3 number 7. If A divides B and A divides C, then A divides BX plus CY, where X and Y are some integers. Finished? So now I can say that D divides 1 because AX plus BY is 1 I have taken. So therefore D divides 1. Okay, so therefore D value should be what? Which number divides 1? Yes, D value should be D is equals to 1. Yes, D is equals to D will be is equals to 1 since D must be positive. Yes, D must be positive. D is the divisor here, so divisor must be positive. And this is since AX plus BY is equals to 1. And this one you will have to write in the book. It is given theorem 3 number 7, but you write the whole theorem 3 number 7. Okay, theorem 3 number 7, you write the whole. That means in here you will have to write that if A divides B and A divides C, then A divides AX plus CY, where X and Y are some integers. Okay, that whole theorem you will have to write it down here. So therefore D is equals to 1. Finished? GCD of AB I have taken as 1. So therefore GCD of AB is equals to 1. Okay, so therefore I can say that A and B are relatively prime. Okay, A and B are relatively prime. So this proof one time again I am showing you. Okay, theorem 5. This is your saying two integers a and b, both of which are non-zero, will be relatively prime to each other if and only if there exist two integers x and y such that ax plus by is equals to 0. So in here two integers are there, okay, both of which are non-zero. So two integers are there. Okay, these two integers will be relatively prime to each other if and only if there exist two integers x and y such that ax plus by is equals to 1. So in here, first of all, I will take let a and b be two relatively, let a and b be two relatively prime integers, two relatively prime integers. That means what I can write? Therefore, GCD of AB is equals to 1. That means GCD of these two numbers will be 1. They are relatively prime integers, so therefore GCD of AB is equals to 1. Finished. Now from theorem 4 I can say, now you can say that GCD of AB is equals to AX plus BY. This is from theorem 4. Okay, you can write it down, this whole theorem 4. Theorem 4 you can write it down in here. Okay, this one I am getting it from theorem 4. Understand? Now you see GCD of AB 1 I have taken. GCD of AB is equal to AX plus BY. So therefore I can say that AX plus BY is equals to 1. Conversely, let AX plus BY is equals to 1 and also let GCD of AB is equals to D. Now GCD of AB is equals to D. Therefore, I can say that D divides A and D divides B. GCD of AB is D. That means D divides A and D divides B. So therefore, I can say that D divides AX plus BY. This is our theorem 3 number 7. This one I am getting it from theorem 3 number 7. Okay, AX plus BY I have taken as 1, so therefore I can say that D divides 1, since AX plus BY is equals to 1. Finished? So therefore D will be is equals to 1, since D must be positive. D must be positive. D is the divisor. Divisor must be positive. So D is what? GCD of AB, D I have taken. So therefore, GCD of AB is equals to 1. So therefore, I can say that A and B are relatively prime integers. That one only, finished. Again, nothing there. Okay. Now these are some of corollary. Corollary 1 saying that if GCD of AB is D, then GCD of A by D, B by D, it will be 1. Next saying that if A divides C, B divides C, then GCD of AB is 1. If A divides C, B divides C, and GCD of AB is equals to 1, then AB divides C. Okay, so these two are corollary. Now I will go to Theorem 6, Euclid's lemma. Okay, Theorem 6. This is some of the theorems I am explaining here. Okay, you just Watch the proofs very carefully. These theorems are very important. Theorem 6, Euclid's lemma. Euclid's lemma. So it is saying that if A divides BC and GCD of AB is 1, then A divides C. Okay, Euclid's lemma. If A divides BC and GCD of AB is 1, then A divides C. Okay, so in here you see GCD of AB is equals to 1. Yes, GCD of AB is equals to 1. Finished? So therefore I can say that AX plus BY is equals to 1. Yes, AX plus BY is equals to 1, and this is from where I am getting A and B are relatively prime, then AX plus BY is equals to 1. That means GCD of AB 1 given, then AX plus BY is also equals to 1. This is from theorem 5. Yes, this is from theorem 5. So GCD of AB is equals to 1. Okay, so therefore AX plus BY equals to 1 for some integer, X and Y. Okay, AX plus BY is equals to 1. Now both side I will multiply it with C. So C this is equals to this become. Okay, C bracket start AX plus BY is equals to C. This one if I multiply it, I will get ACX plus BCY is equals to C I am getting here. Okay. So now you see A divides BC. Yes, A divides BC. This is our given. A divides BC. This is our given. Okay. And A divides AC. A will divide only AC because A factor only there. A into C. A will divide only. Yes or no? Finished. So A divides BC and A divides AC. Okay. So therefore I can say that A divides ACX plus BCY, and ACX plus BCY is equals to C. So A divides C, and this is our proved. This is again theorem 3 number 7. That much only. Again in here nothing there. Understand? Next again you see Euclid's algorithm. Next it is Euclidean algorithm. Euclidean algorithm you have already learnt in general mathematics. This is lemma 1, saying that if A is equals to QB plus R, then GCD of AB it is equals to GCD of BR. Okay, so this is A is equals to QB plus R, then GCD of AB will be equals to GCD of BR. So in here again you see this is proof. Let GCD of AB is equals to D. So from this what I got, that D divides A and D divides B So D divides, this will be in here, you see D divides ax plus by, yes or no, ax plus by for some integer x and y. Now instead of writing ax, I will write here a into 1 where x value is 1, okay, plus ax plus by, yes, b in place of y I will multiply it with minus q. So this is, I will get D divides a minus bq. Okay, a minus bq means this is a is equals to qb plus r given, yes or no. Now this qb, if I bring it to left hand side, then I will get a minus qb is equals to r. That means a minus qb or bq, same thing only. That means a minus bq value is what? R. So in here I can say D divides R. Finished. This is our theorem 4. This one, wait a minute, theorem D divides A and D divides B, then this is our theorem 3. Okay, D divides A and D divides B, then D divides A x plus by. This is from theorem 3. Okay, theorem 3 number 7 in the book, theorem 4 number 7 given. This is theorem 3 number 7. In the exam hall, you write the whole theorem here, okay, where x value is 1, where x is equals to 1, and ax plus by, y is equals to minus q. X value 1 taken, y value minus q taken. Understand? So this one I got. This is r, since a is equals to qb plus r. Finished, done. D divides a minus bq. How I got D divides r? Because from here, if qb, if you send it right hand side, then you will get, sorry, left hand side, then you will get a minus qb is equals to r. A minus qb or bq, whatever you say, a minus bq is equals to r. So therefore this r value I have placed it here. Understand? This one I got. Now next you see D divides R I got. Okay, so in here I can say that does D is the common divisor, D is the common divisor of, D is the common divisor of B and R. Okay, D is the common divisor of B and R, because D divides B and D divides R. So therefore I can say that D is the common divisor of B and R. Now let C be another, let C be another common divisor, let C be another common divisor of B and R. Okay, D common divisor of B and R we have got. Now I will take, let C be another common divisor of B and R. Finished? So therefore I can write that C divides B, therefore C divides B and C divides R. So therefore C divides therefore C divides BQ plus R into 1. Okay, C divides BQ plus R into 1. This is again theorem 3, where x is equals to q and y is equals to 1. Finished. C divides B and C divides R, so therefore C divides BQ plus R into 1. Finished. So now in here you see BQ plus R, this is what? BQ plus R or QB plus R, same thing, only this is equals to A. So therefore C divides A, since A is equals to BQ plus R. Finished. So therefore I can say that C is the common divisor. C is the common divisor of A and B. Yes, C is the common divisor of A and B. Okay. But D is the greatest common divisor. D is the greatest common divisor of A and B. Okay, D is the greatest common divisor of A and B. So therefore C will be less than equals to D. Okay, C will be less than equals to D. So thus I can say that thus D is a common divisor. D is a common divisor of B and R such that any common divisor C of B and R is less than D. Such that any common divisor C of B and R is less than D. This one, therefore D is equals to GCD of BR. So therefore I can say that GCD of AB is equals to GCD of BR. This is our done. Okay. So in this video we have discussed theorem 4. Theorem 4 proof I will give you, but not in this video. Theorem 4, very important theorem this one. Theorem 4 states that for two integers a and b, at least one of which is non-zero, there exist another integers x and y such that GCD of AB is equals to AX plus BY. Next, it is relatively prime integers, that means the GCD of AB is 1, saying that this is theorem 5, two integers a and b, both of which are non-zero, will be relatively prime to each other if and only if there exist two integers x and y such that AX plus BY is equals to 0. From theorem 4, this one, first one it is corollary 1 and the next it is corollary 2. Next one comes to theorem 6, Euclid's lemma. If A divides BC and GCD of AB is 1, then A divides C. And the last that we have discussed, this is Euclidean algorithm. If A is equals to QB plus R, then GCD of AB will be is equals to GCD of BR. Okay, very important theorem. So in the next video we will discuss lowest common multiple, LCM. These examples I have already solved it. Okay, example 9 and 10 is left, and exercise 3.3 I have already done. Just in here type 6 and type 8 some problems are remaining. If these are over, then your half-yearly syllabus will be over. Okay, these theorems I will discuss it one more time in the revision. Don't worry. Okay, we will discuss it one more time. So I hope you have understood. Thank you.